Hello, how's it going today? I remember like last section we're talking about many different discrete distributions like Laplace distribution, binomial, negative binomial, geometric, uh, and yeah, and especially the uh Bernoulli distribution, which is the easiest type. And we left the Poisson distribution not talk about, and today we'll introduce Poisson distribution in discrete probability. Usually the Poisson distribution is viewed as in a certain amount of time, there's a constant rate of people entering into that building. Not like people entering building, probably like what about like water entering a bucket? But usually it's like there's a rate of something drawing into a space. And when that rate is fixed, like what is the expected how can we say the distribution of the number of the objects that enter into the space given that rate? So that is Poisson distribution. But here today I want to introduce it in a different way. Like we are viewing Poisson distribution as a long-term behavior of the binomial distribution. So for large n, when n in a binomial distribution become very large, it's very difficult to compute because of this combination, the n to a, this combination will become very, very large. So and for this the combination, it is like the factorial of n, k, and n minus k. If that grows large and we are not really able to calculate that out, even for your computer, it will be very heavy. So we want to find out another way that don't contain the factorial, don't contain like the factorial, so it's easier to calculate. So we would like to define a new variable, the new random variable x, whose distribution is the binomial NP for large n. But this time we're not say it's binomial. It is because binomial distribution means the n is limited, but here we want to n to approach to infinite. So, and in this case, for all of the k equals to the integers, so it is still discrete. You cannot say k equal to 0 point something or 1 point something. So in this case, the limit of n goes to infinity for the probability that xn, like the sequence of the binomial distribution equals to k, is equal to e to the power of negative lambda times the lambda to the power of k divided by k factorial. So in this case, we don't have n factorial, we only have k factorial. So, and the k is definitely smaller than n, so we are reducing our computation complexity. And moreover, notice here that this is the mass function. The function is a probability mass function, and for it is on 0, 1, 2 on the integer set. This can be solved immediately, and that is not a I don't think that it is really worth to talk about here, because we'll see how it can be applied later on. And another thing is how we can prove that y goes to infinite, yn goes to infinite. This probability will limit into the thing. So here we like to think about one common issue is we let the k equals to the natural number union with the 0. So this set is like it's the non-negative integer. So why we include 0 is because in the binomial distribution, k can equal to 0. So we want to include this term. And also maybe here we are not familiar with what is lambda. Lambda is n times p. It's the probability of the binomial distribution times the n, which is the number of observation inside. So that's the lambda. And for here, so we are going to view about the proving process of this formula. And we already know the case any non-negative integer and the probability that xn equal to k, which is here, x1, x2. It's a like process, but we are not explaining it that way. It's a sequence of binomial. So each of them have different output. So xn equal to k is become, this is directly the formula of binomial distribution. So so we can expand this term out as here the k factorial is still the k factorial, but like on the upper side, the n times it has. So explaining this term out, it has n factorial on the upper and have k factorial times n minus k factorial. And once we can, because the n factorial contains the term, contains all of the terms inside n minus k factorial, so we can just left what's after the n minus k factorial. So it's n minus k plus 1 times n minus k plus 2 times n minus k plus 3, and all go along the way to n minus 1 and times n as the last term. So we can see here this term are reduced by 1 factorial, and here we just copy that down, and obviously when n goes to infinite, which means like n divided by n is 1, but n minus 1 divided by n also goes to 1. This is because n is very large. So infinite minus 1 divided by infinite is still infinite divided by infinite, so it's still 1. And all of those terms here are equal to 1. And this is the separation. And this is the separation of all of those terms ahead. And we add n to the power of k below. So if we divided one additional n to the power of k, we need to multiply that term later. So we multiply here p times n to the power of k. So, and remember, p times u becomes the lambda, so it becomes lambda here. And this term were reduced to k factorial, 1 over k factorial. And of course, this term, we are left with this term. And so we want to find another term which can like linked with this formula together. So we are trying to mimic the e to the, well, trying to mimic this term. And remember, we can absolutely times the n both on the numerator and the denominator, and this is 1 minus p to the power of n. But here's n minus k, so we just divided 1 minus p to the power of k. And we can see this term goes to lambda to the power of k, and this term goes to e minus lambda, because this is the process here. Because everything, we can say 1, because everything was like 1 minus x divided by n to the power of n can be written as the e to the power of minus x. So here is and so here is 1 minus n, the lambda divided by n. So and to the power of n. So here we can write this term as e to the power of minus lambda. And the last term, because also remember, like this is p, but here because n goes to infinite and np has a value, so p is go to 0. or like the limit of p when n goes to infinite is 0, or other. If that's not the case, then it will not have a value. So because p, the limit of pn is goes to 0, so 1 minus p, 1 minus 0 is definitely 1, and 1 to the power k is 1. So this term is also 1. So as a result, we combine those terms together, we time them out, and we find it's like this becomes the e to the power of minus lambda times the times lambda to the power of k, which is here, and left with the denominator k factorial. So that's the case in this proof. And remember, like when we want to show that a certain function is like if we want to show it's a probability mass function, then it has something we need to prove too. Like every term, first of all, like every term is greater than 0. So no matter what value k takes, the probability of that should greater or equal to 0. And also, we want to find out when we sum up all of k from 0 to infinity, and it goes to 1. So that's the definition of like a probability mass function. And want to show if that's the case. And for the first property, k greater than 0, we can find in this formula that k, because this is e to the power of something and is positive, so this term is definitely positive. And if k is a value like greater or equal to 0, this term is positive and this term is positive, so it definitely cannot be negative. And this have already been proved out that every k brings us a positive value. But for this term, want to prove the sum of k from 0 to infinity times this term. Like we sum them up for k from 0 to infinity, and this is equal to k k factorial k under the lambda to the power of k times e to the power of negative lambda. And this term it should prove to be 1, but I don't think it is very important here to show y is equal to 1. So I will just continue with the next content, the Poisson distribution. So a discrete random variable x has a Poisson distribution with parameter. There's only one parameter, the lambda, and it should be greater than 0 because we are trying to get it by multiplying n times p, which is both positive. So and we can calculate this probability mass function by p, the probability of like any term, any cases equal to k, and this is the e to the power of minus lambda times lambda to the power of k divided by k factorial. So this is the distribution of Poisson. And we have derived the Poisson distribution via limit argument. But another way for Poisson distribution is what I talk about just before. Like the lambda is like a rate. The lambda is the rate of the uniformly distributed in time and space. So for example, there's like and there's on a certain crossing, there's five cars per second to pass that crossing. That's the average rate, and that is lambda. And we want to find out how many cars will pass that crossing in 1 minute. So that is like 60 seconds in a minute, and we know that the average rate was 5. So what's the expected value for 1 minute? Well, just calculate the average, the expected value for every second, which is absolutely 5. And we can And we find out that value was 5 and times 60, which is 300. And that is like the expected value calculation of the Poisson distribution. But for the distribution, we'll say, well, if k equals to 1, that's the probability of just one of like during a certain second, there's only one car passing that crossing. And if k equal to 100, and that's the probability that 100 car just passing that crossing during that certain second. But the next example we're gonna see is still like using the Poisson distribution as a limiting behavior of the binomial distribution. So suppose a book have a typo with small probability. So this probability of having a typo on any pages is 0.002, and there are 100 letters on a typical page of the book. So what is the approximation distribution of typos in a single page? So in this case, this is a binomial distribution because we can know n is 1,000 and p is 0.002, because if we have a typo, that means a success. If we don't have typo, that's a failure. So that's the case in this question. So what we do before is to use the binomial the model, but this model can be very tedious because we want to find out what's like 1,000 to like some like k, for example, k to the power of for example, if k equals to 700 and it's 1,700 combination times 0.002 to the power of 1. No, that's like 7,000 to the power of 0.002 times another 300 to the power of something, but that will be very, very hard to calculate. So an alternate approved the process is by using the Poisson distribution, which is a approximation. And in this case, we can easily calculate that out because we know the lambda is n times p, and that is equal to 2. So Poisson 2, by plugging k equal to 2 in this formula, and we can get a nice formula easily in this way. Okay, so that's the all of the all of the 7 very common discrete probability model. And we're moving to the next section, which is the expected value and variance of discrete random variable. We're all talking discrete because here we're not touched with the continuous random variable yet. So discrete means, like, for example, in Poisson, the x can only be 1, 2, 3, 4, but cannot be all of the real numbers. But if it just equals all of the real numbers, then it is a continuous random variable. So that's the difference. And for expected value, I think many of you have already know that from very young age. Like it's like the expected thing to see in the long term, and that's more like an average value, and that is what we are going to explore today. So the first example we see is a roulette game. The American roulette has the number 0, 00, and 1 to 36. So this game is playing in this way. If you bet any number, if you bet any dollar on the number, and if the number comes out, it's an even number, and you win. And if it's a odd number, you lose. But here the even number doesn't include 0 and the 00. If that's the case, then you have like 20/38 chance to win, but only have 18 over 38 chance to lose, and that will cause like a bankrupt of the game company. So they count as 0 and 00 as odd number. So that's an odd behavior, odd rule to for setting up the game. So in this case, you play 38,000 times, and you are expected to win about 18,000 times and lose about 20,000 times. That is the expectation based on the probability. So the expected payoff per game. So remember, in this case, you bet $1 on even, and that means you win $1 if you rolls out an even number, and you lost one number if rolls out was an odd number or 0 and 00. So the expected payoff of the game is easy to calculate. It's just like 1 times 18,000 minus 1 times 20,000 divided by the total number of times that you play, and turns out to be slightly negative. And that's the reason why those roulette game company can cooperate and running until today. So on average, you will lose about like $0.05 per game, and that is acceptable within very short term. But in the long term, you will continue losing when this base goes very large, and it times 0.05, and it also goes very large. So here we introduce the expected value, the rigorous definition of expected value. It is first, we need to check whether it exists, because if the sum of all of the x, sum of all of the cases, the x cases of the probability that x happens times the absolute value of x. If that case was infinite, then we are not able to calculate that out, because as long as one term is infinite and we sum them up, and we cannot know the exact value of this term. So based on the real analysis, if you change the order of that addition or summation, then the alternate value will vary around the infinite. So that in that case, we cannot calculate the expected value. But if the sum up of all of the x times the absolute value, because it can go positive and it can go negative. So we use absolute value to balance that out. And if the absolute value times the probability of x is smaller than infinite, which means it's finite, then we use this formula to calculate that out. And this is very reasonable, commonsensical, because you have the probability that some value occurs, and you sum up those probability altogether is equal to 1. And they are like different ratios that given to the output, and that's the formula for the expected value. And one thing also to notice is that the expectation of x is not a value that's likely to be observed. Because, for example, in the first case, you are not expected to lose exactly $0.05 in one deal. You can only lose -1, but that's like a long-term average. If you use that number to times, for example, 38,000 times, and you will get what you will averagely lose for the 38,000 times. Okay, so based on the discrete probability model we discussed last time, and including the Poisson today, and we'll calculate their expected value one by one. So the first is Laplace distribution. So what is the expected value of Laplace distribution? So based on this formula, we will always use this formula as our basement for for finding out different models expectation. And because the the probability for Laplace experiment is 1/n. And I remember like all of the n are from 1 to n. So with so the k here, the k here or the x here is just from 1 to n. So we sum them up, it's very easy. It's just like it just sum n to the we can use the summation formula to use the first term plus the last term times the half of the term number, and this will produce 1 plus n divided by 2, which is I would say logical based on Laplace distribution. And for the Bernoulli distribution, it's also very simple because the x can only be 1 and 0 in that case, and it has p to be 1 and 1 minus p probability to be 0. So the expectation of x is 1 times p plus 1 minus p times 0, which is 0. So it's just p in the Bernoulli distribution. So now we are seeing the binomial distribution. The binomial distribution is somehow like more advanced to calculate its expected value, but it can be solved. So first we list out the probability of the when x equal to k, and this formula is from the last lecture slide, and we can see that the expectation of x, this value is k times that, and it's from 0 to n because k cannot go negative and cannot go larger than n. So that's all of the possibilities of k, and that's we can say that's the realization of x here, and because like when 0 times something, it goes to entirely 0, so we can eliminate 0 out to be 1. And so the next step is the mysterious step, because we convert a k times the combination n to k to n times the combination of n minus 1 to k minus 1. And this mysterious case is doing here. So first of all, we say that this term can be written as this term to expand it, and then once we expand it, we can divide the k out and move 1m out. So m to m factorial becomes m times m minus 1 factorial, and k factorial, because the existence of the k, it becomes k minus 1 factorial, and in this case, the last two terms n minus k, we can minus both of the term by 1, so n minus 1 minus k minus 1 factorial. And this formula, if you look very familiar, is equal to n times this formula, which is the combination of n minus 1 to k minus 1. And we are converting, and now we are converting this combination to another combination. And for this term, we can move something out, like because n and p doesn't contain the k term, so we move n times p out. And inside that term is n minus 1, k minus 1. And because we move 1p out, it's only have a p to the power of k minus 1, and times 1 minus p to the power of n minus 1 minus k minus 1, because if we minus both of the terms, it doesn't affect the result. And now we can say that this is exactly the formula of another binomial distribution, which is like which the p is still p, but the number of n becomes n minus 1. And we know that the summation of all of the cases for one binomial distribution is 1, and we have NP left out. So the value is NP times 1, which is N times P. So the expected value of any binomial distribution is N times P. Okay, so let's see another, the Poisson distribution. The Poisson distribution is largely, I would say, largely the same thought, the same logic. So first we'll use the formula to use the K realization, but to consider all of cases of the realization times the distribution, and this can become this term because the K, the same reason, like if K equal to 0, the entire term becomes 0 and it can be ignored. And the next step is to combine the K combined together. Why we always think about that? Because compared to the previous cases, what we do is to try to form a new company, a new distribution, which is also the sum of all the realization of that distribution. So it is 1. So we can know that's if we can know that's 1, and we don't have the summation sign outside, the sigma sign outside. So we can just use 1 times that term to left as our result as the last term. So that is so I think that is straightforward. So once we find K and K factorial, we use the K to divide it to trying to find another Poisson distribution, but with smaller K. And once we are done here, and it's straightforward to remove the lambda out. So it's lambda K minus 1, and this is absolutely, we find out it's another new Poisson distribution. So this is equal to 1. So the expected value for Poisson distribution is lambda as a result. So I want to talk about more about the expected value, because sometimes we're not only interested in how the P or how the X, the realization behavior, but sometimes we have a formula for, we have another function ahead, like on the top of the realization. So let's say there's a function gx, which converts the random variable to the real number again. And this is a new function, so that the summation of, and we know that it cannot, the summation of all of the realization times its probability will not be infinite. So the expected value is gx times px, and this becomes, and if we sum them up, this becomes the final version of our expected value formula. It looks somehow familiar, I would say, because previously this is x and here is x, but now it's gx, so it's just changing, it's just plugging another layer of function inside. It doesn't change. And if you want to prove, you can see here's a proof of that theorem, but I don't really think that it's very complex compared to the proof we've done before. And of course, if you're interested, you can view this slide for longer. But the main idea of this proof is just to use the functions bijection probability, like to use the domain and range to exchange it. And now let's see one example. So we already know the distribution of the Poisson distribution before, and now we want to compute the expected value of the Poisson distribution. But now this distribution is in another larger function, which is like e to the power of t times this distribution x. And we want to find out what's the expected value of that sign. So I would say one common approach for that is it's just use the transformation formula above here, and the gx here is e to the power of t times x, and the fx here is, or I mean the probability function is the Poisson function. It's the later half. So now we're just like calculating this term out, and it's not very hard to calculate because we can firstly combine the e term and move it up. So it's lastly calculate that term out. And I think one important step inside this process is this step. It's like how we are moving from this step to this step. This can be somehow like not very obvious because we're now using the property we studied before. I mean, in the last page, yeah, we are using this property because remember, here's 1 minus something. Although like the 1 is not a curve, but it's minus something here. So so this term can be calculated as e to the power of the center term. So this is the definition of the of how we treat exponential function. And we are done. And the next property is the triangle inequality for the expected value. So so why we want to like so obviously before we can already calculate directly calculate the exact value of expected the expectation, but sometimes this formula or this properties is not really available to reach for us. So we need to use some inequalities, try to mimic the upper bound or lower bound of the expected value, so we can get a sense of how large is that expected value. So the first and the simplest formula for estimation is the triangle inequality for the expected value. It's written as this form. It's like the absolute value of expected value is smaller or equal to the expected value of the absolute value. Okay, so this looks like very obvious, because if every realization is in the absolute form, it's adding every positive term. And here we can add some negative term in between, which will decrease its value, but after that we sum it up and turns out to be positive. So that will be like closer, or I mean like less distant from the origin than this value. So intuitively it's correct. And the proving process is very simple. We just use the expectation formula to plug in the realization of absolute value of x. And because px is a probability, it can never go negative. So we can expand the absolute value to here. And this step, we are using the triangular inequality for real number addition. So the sum of every absolute value is greater or equal to the absolute value of the summation of each subterms. And this turns out to be the absolute value of the expected value, which is in the last step. Okay, and the last property of the expected value is the linearity. So if x, y are discrete random variables whose expected value exists, so x and y are discrete random variables, and and now we're knowing their expected value. So we can use the linearity to calculate, like the AX is equal to, we can move the A out and calculate the expected value of X. And if they are plus together, we plus their expected value separately. And for any constant B, we are just using the B out. So that is very direct. And the ultimate formula for the linearity of expected values here. So if we can find out a1x1, a2x2 to anxn plus b, and that can be converted to here. So that's directly the linear combination of or like the linearity of anything, and we just treat the expected value as a function. And these two properties can be easily proved here, and the proving process is here. But I don't think illustrate why the correct is very reasonable, because I think they are super easy. Like for the first property, you just move the A out, and that's very direct. And for the last one, because P is a constant, so there's like only have probability of 1 for B occur, and it has probability of 0 that B doesn't occur, or like the B is when Y is not equal to B, it's not possible, so it's 0. So yeah, you can have a look for this page, and the property of the second property is harder to prove, and we're not able to doing that for now. Okay. So if we know that the linearity of the expected value, we're now able to use that to quickly calculate the expected value for binomial distribution. Because remember before, when we are calculating the binomial distributions expected value, we're using nearly like 2 pages of the slides to separate all of the terms inside the P or 1 minus P out. And that could be, and that is not, I would say that is not efficient way if we can use the linearity. So in this part, yeah, so we know the binomial distribution is a combination of it's a summation of all of the Bernoulli distribution. Then we can find out. Then we only need to sum up all of the n terms of the Bernoulli distribution result. So okay. So each of the Bernoulli distributions expected value is P, and there's n terms. So we have n terms of the P that's sum up together. So it's P, so it's just like n times P. So we're done. Okay, and I think today we're like running out of time. So variance will be talked about in the next week.